Welcome to the channel. This is our fourth video in a pre-calculus review playlist for calculus course. And we're going to talk about logarithm functions. Basically the definition, how they are the opposite or inverse of exponential functions. We're going to talk about the two different types of log functions, which is base 10 and base e. There are other bases, but these are the most common, as well as the properties of logarithms. Just a brief review over these things. So you know what they look like and kind of how to work with them. So we're just going to try to define what a logarithmic function is. It's not as intuitive as an exponential function, which we talked about 2 videos ago, but a logarithmic function is the inverse of an exponential function. Just like if I have a parabola y equals x squared, well, the inverse, which we might denote f inverse to the minus 1 power of x, equals square root of x. And let's call this f of x again, y, f of x, they're all the same thing. So a logarithmic function is the inverse of an exponential function. So I do recommend you check out that video 2 videos ago, I'll place a card, that defines an exponential function, because it's much easier to think about that with data and try to understand it in a real world application. But we don't do that with logarithmic functions. We just think about it as the inverse. So let me write down the population function that we derived from the data in that video where we said, well, p of t, the population is a function of time in millions, populations in millions, and time is in years. Well, if it increases at a 3.4% increase year over year, this is the function, the exponential growth function that describes it. But now we say, what happens when we solve for t? I want to know not what the population is after 20 years. So if t equals 20, we know that we can just simply plug it into the equation and figure out the population in millions after 20 years. Great. But what about if the population is 30 million and I want to solve for t? So let me write it out for you. The problem we want to solve, 30 equals, notice that we're saying 30 million. When the population is 30 million and it equals this, well, what year does that happen? So I want to solve for t. And we need to use logarithmic functions to basically get t, kind of extract it out of the exponent. Because we can't simply do our basic division and multiplication, addition to solve for t here. We need to do something very special and take the natural log, or log base 10, we're going to talk about both, of both sides. So let's talk about something called log base 10. And what it ultimately means is, in the context of an equation, log base 10 of x equals some number, let's call it c. Well, we usually write this as simply log x equals c, where the 10, the base 10, underneath the log here, which I haven't written, is just implied. When there's nothing there, it is log base 10. Notice that I could have any other number. I could have log base 5 of x equals 25, or 2, let's make it. I could have log base 1.1 of x. I could have log base 100,000 of x. All of these things, I can put any number there. Don't get too hung up on that, because we only really use consistently log base 10, which again is just this, log nothing x, or log base e. So this is a very important one, which we're going to talk about next. Log base e is actually defined as, let me include an x there, it's defined as natural log, or ln of x. Notice there's no e there, and we don't use the words log, or the letters log, log, we use ln of x. So that's what we're going to talk about the next section. It's these two here. These are the most important ones that you need to worry about. So log base 10 of x is defined as log x. Okay? So the 2 boxes here are what we're going to talk about. And the last thing here, because you've spent a lot of time on this hopefully already, normally we would solve all kinds of equations, go into it a little more depth, talking about how it's the inverse of an exponential function, but we don't need to do all that here since it's just a review for Calculus 1. But remember that if I have some equation where I say log of x equals 3. Well, remember, there's a 10 implicitly defined here, and we can rewrite this thing as 10 to the third equals x. So x is equal to 1,000. That's how we would solve this equation. So just remember that. I always tell myself, let's do a different one, even though we don't use it very often, but log base 2 of x equals 3. I say to myself, how do I solve for x? Okay, well, it's the base to the exponent equals x. So let's be very careful here. And I'll do a color coding, and then we'll move on. So I always tell myself base to the exponent on the right-hand side equals x. So that means that 2 to the 3 is equal to x. That's how you solve these equations and deal with logarithmic functions in general. That's the easiest way to do it. And just remember, log base 10 is just log, and then now we're going to talk about the natural log again here, but do a little more with it. Remember that log base e of x equals c. This means e to the power of c equals x. And this will be the last time you'll ever see me write log base e like this. Just a reminder, we always write natural log, means log base e, of x equals c, and it means the exact same thing. E to the c equals x, okay? But now let's talk about the tables and graphs related to these equations. So if I were to graph this, let's use x and natural log of x. Okay, that's what we're talking about, this log base e business. Well, it's undefined at x equals 0. That's always true for any log function. It is not defined at x equals 0. There's actually a vertical asymptote at x equals 0, which we'll see in a minute. When x equals 1, well, it's 0. That's where the x-intercept is when x is equal to 1. And as we go down 2 and down to 10 here, we see that the natural log of x, well, it's the natural log of 10, which is a very small number. And this is 0.3 roughly. These are infinite numbers, infinite decimal points, but you can put in a calculator and see that. But if we do the inverse of the natural log of x, e to the x, well, doing the same thing, we can see that it's defined for all x. And as we go, we get e to the 0 is just 1, e to the 1 is e squared, e to the 10th. That's a pretty big number. Remember that e is just like pi, 2.71, whatever it is forever. And 2.7 to the 10th power is fairly large, much larger than the natural log of 10. So what we want to get out of this, if we were to plot these things on the same graph here, x and y, well, since they're inverses of each other, we just learned that they are reflected about the line y equals x, which would be this one. And so e to the x, hopefully, you know that there's a y-intercept here, we just found that, and it approaches 0 as x goes to negative infinity, and it gets really big really fast. That's the nature of these exponential functions. This one, again, is e to the x. And now the natural log, there's a vertical asymptote here, so it never touches this axis, and it crosses at 1, 0. It never touches, and it kind of grows slowly, something like that. So that's the natural log of x. So this has very slow growth. All log functions have very slow growth, and exponential functions have very fast growth. That is the hallmark of these functions. Remember that a logarithm is an inverse of a exponential function. The last thing I want to talk about in this video before I do a very short example involving logarithms is the properties of logarithms. So there are essentially 5 that you would like to know that are very important, and we're just going to write them down and talk about them because, again, this is a review. So we'll use natural log since that's a little bit more common than anything else, where a and b are simply just numbers. A could be 2 and b could be 3. Well, the property says that this thing is equal to the sum of each natural log, like that. That's the first property, sometimes called the sum property. We also have a subtraction property. Let's divide these two numbers, a and b. Then we have natural log of a minus natural log of b. So if we're multiplying inside the argument, that's what's inside the parentheses, we call it the argument, For multiplying two numbers, well, we can add them and separate the logs, okay? That's all it is. And the same thing with division. If we're dividing two things, we can subtract them and separate the logs. There's a few more here, so let's do the natural log of a to some constant, p, okay, in the argument. Well, that means that we can bring p down in front, so p times the natural log of a is what that becomes. I want to say something else here is that I don't care what the base is. Note that natural log is log base e, but if it was log base 2 of x times y, the same property applies. So I don't care what the base is. This becomes log base 2 of x plus log base 2 of y using the properties. So that's nice. You don't have to remember different properties for different bases in our logarithm. It is always the same property no matter what the base is, okay? So keep that in mind. This is not just for natural logs. So we can also say that if we take the natural log of e to the x in the argument, this is just equal to x. Let's see how that is using this property, using property 3. So x comes down in front, and it's the natural log of e. But the natural log of e is simply just 1. And so that is why we can say that natural log of e to the x is simply x. And the last most important property that we're going to talk about is kind of the inverse of number 4, where let's say we take e to the natural log of x. Well, this is also just equal to the x. And that makes sense if we're taking the inverse of a function. We know that the exponent is the inverse of the logarithm, so it should just give us x. The same as taking the square root of a square gives us just the number, because it's an inverse property. Now, a few other things I want to write down here. Log is never defined for x less than or equal to 0. Log whatever base is not defined, does not exist. It is outside the domain of these functions. Make sure you keep that in mind. It is only defined for positive values of x. Now, if we are transforming it, that's a different story, but we're talking about the parent function, natural log of x, or log base 3 of x, just a normal log with x. And one other thing is that log, say log base 10 of 1 is equal to 0. So these are kind of your secondary properties, a and b. And so this is always true because, well, let's rewrite it the way we do. It's 10 to the power of 0. Well, that is equal to 1, of course. So any log of 1 is always equal to 0. Because of this property here, anything to the 0 power is equal to 1. And I want to end this with a very quick example. What makes this useful that you're going to be doing it all the time in calculus. They expect you to know everything we talked about and even more in depth here. I'm going to try to add more videos on a pre-calculus course if you need more in-depth examples and work-throughs. But let's just solve for t. Notice that we can't just multiply or divide or do anything. The t is in the exponent, so we need to remove that exponent. And so what can you do? Well, let's take the natural log of both sides. Notice that I don't care if you take log base 3, log base 10, log base 1,000,000, it doesn't matter what the base is. Natural log e is just nice and easy for my calculator. But as long as I do it to both sides, it doesn't matter. And then going back and using the third property here, as I'm pointing to in a red arrow, well, it says if I have an exponent in the argument, it comes down out front. So that means that, this is equal to t natural log of 2, and I still have natural log of 7, of course. Now this is t times natural log of 2, so solving for t, we can do our normal division finally and say t is equal to the natural log of 7 divided by the natural log of 2. And like I said, I don't care what you use, so this is also true, as you can verify. Log base 3, log base anything, t is going to be equal to that, which is a very kind of counterintuitive thing, but when you start understanding how logarithms work and how they are simply an inverse of an exponential function, we see that it doesn't matter, okay? Try to spend some time on this. You don't need to get in the weeds about solving equations like you did in pre-calculus. You spend enough time on that, but you do need to know how to isolate a variable using the properties of logarithms. That's sort of the most important thing that you'll need to carry over into calculus. And certainly what the parent functions look like for exponential functions, something like that, where you have your intercept, and the parent function of a natural log or log function, okay?